infinite geometric sums, we have a little story. So I went to Snow College almost 30 years ago and started, my calculus and some important math classes there. I had some very awesome professors named Ted and Bart. They happened to be the same teachers my sister had when she was at Snow College. They actually called me her name all the time, even though she's 15 years older than I am. I was like, good heavens, it's been 15 years. I may look like my sister, but haven't you forgotten her by now so that you can actually know me and call me by my name? Anyway, none of this is relevant, but you know me in stories. So Bart used to like to explain this notion of an infinite sum by saying, let's suppose we have a pond. And we have a frog on one side of the pond that wants to get to the frog on the other side of the pond. But let's say for some reason he can only hop half of the distance each time. So he starts by hopping. Okay, let's see if I can make a smaller frog that will help me here. Thought my story was all ready to go, and then I decided to change it up. So I'm going to take this little frog here. Oops, the whole thing is joined together. This guy, yeah. And we're going to have him start here. Let's move him to the front. Okay, so he can hop half the distance. So he's moved 1/2 pond so far, right? Then he can hop half of that distance. So now he's hopped 1/4 of the pond on top of the half of the pond that he's already hopped. Well, now he can hop half of that distance. So now that's 1/8 of the pond, right? And then hop half of that distance, which would be 1/16 of the pond. And hop half of that distance, which would be 1/32 of the pond. And eventually these numbers that he's able to hop across get so small that he's pretty much there to see his girlfriend frog, right? So all in all, even though he never quite gets there because it's just adding smaller and smaller numbers, it's so close that we just call it one pond because these numbers practically add up to 1. They add up so close to 1 that we can just call it 1. Alright, so the geometric sum for an infinite number of terms can be found with this formula. Infinite sum is equal to a sub 1, the first term, over 1 minus r, the common ratio. Yes, this is a simple formula. And it's also pretty easy to work with as long as you remember the copy dot flip stuff for simplifying fractions. Okay? We have a couple of words we need to talk about. One is converges. When a series converges, it means it has an infinite sum. It converges to a specific number. If it does not have a sum, it's said that it diverges. It does not have an infinite sum because the number just keeps getting bigger. There's no way to put a number to that. So the type that converges happens because r is less than 1. So r, their common ratio, is a number less than 1, which means when we multiply that times each term, the following term gets smaller. And eventually the numbers get so small that it's like we're adding 0, so that our frog is getting to his girlfriend without any problem because 0 distance, even though it's not. Alright. There's some vocabulary for you and just the idea, the notion of how we can have an infinite sum. Alright, let's go to some examples. These look really ugly. Let's just start fresh. Clean off this page. Have my notes in front of me, so if I start to question something, I can just look it up. Okay, we've seen this sequence before, haven't we? We just saw it as a finite sum, but now we're going to look at it as an infinite sum. The finite sum to 11 terms, if I recall correctly, was approximately 3. However, if we keep adding terms, an infinite amount of terms, then eventually pluses and minuses will cancel out, and we will converge to a different sum. Let's see what that sum is going to be. I just like freaked out my computer. Let's see if I can get it to work. Sorry, I can go back to this page. Here it is. All right. All we need for these infinite sums is a over 1 minus r. I'm being a little lazy because I'm not writing a sub 1. It's assumed that a is just the first term if you don't do the sub term. Okay? So we have a equals 5. We have r equals negative 1/2. And boy, is that negative important. You'll see why. So for our formula, for our infinite sum, we're going to do 5 over 1 minus negative 1/2. Now the reason that negative is so important is if you thought it was a positive 1/2, then it would be 1 minus 1/2, which is 1/2. And then 5 divided by 1/2 would be 10, and the sum would be 10. But because it's negative 1/2 and the numbers are alternating positive and negative, that means there's a bunch of numbers being subtracted. So the number is not going to be 10, it's going to be much smaller than that. So this ends up with 5 divided by 3/2, because our subtracting a negative 1/2 is the same as adding 1/2. So 1 plus 1/2 is 3/2. Copy dot flip, so we're multiplying by 2, dividing by 3, gives us 10/3. Guess what that number is? That is 3.33333 repeating, right? What was the answer we got to 11 terms? Let's go back and look. The answer to 11 terms, I think I went too far, was 3.334960938. So a little bit more than 3.33333 because the last number we put in there was added. So then another number would be subtracted, and this would come down a little lower, right? Etc. So finite sum on the last page, infinite sum here. Slightly different formula, slightly different answer. All right, here I am. Got lost there for a minute in my slides. I like colors for what I write so I can differentiate it from what was already here. I hope you're okay with me taking a second. I know some of you just like fast forward through this little stuff. Okay, here we go. We are going to find the infinite sum. A is 2/3. R is 3/2. Make sure you're actually starting at 1 and going to infinity. It is. So starting at 1, going to infinity, so we're good. So the first term really is 2/3. If it wasn't starting at 1, like if n was equal to 0 or something like that, then a would be a different value because it would be multiplied by this to the negative 1 power instead of to the 0 power. So just be really cautious to make sure that that starting number is always 1 because that could change your beginning number. All right, so we have a over 1 minus r, so that's 2/3 over 1 minus 3/2. That gives us 2/3 over, well, subtract 3/2, that's like 2/2 minus 3/2, so that's a negative 1/2. So that gives us 2/3 times negative 1/2. Is it possible for us to converge to a negative sum? Yes, it is. So multiplying those together, the 2's cancel out. I'm left with negative 1/3 for the sum. I'm looking at my paper, and it has a conflicting answer. Let me think about this for a minute. I just figured this out. So the formula itself worked fine, right? We got an answer. We thought we were right. Here's the problem. This formula only works if r is less than 1. Scratch that. Look at r. R is 1.5. R is greater than 1. That means that this one diverges. It does not exist. It does not have a sum. Because the sum just keeps getting bigger and bigger. So why did we get an answer when we used the formula? Well, we used a formula. We plugged in numbers. That doesn't mean it works if it doesn't fit the specifications of the formula. All right. This one is the one we just did. I could have just moved that stuff over and been good to go. Well, not quite, because the number was off. So we have a over 1 minus r. So 3/2 is our starting number. 1 minus 2/3. 2/3 is less than 1, so we're good to go. So then we have 3/2 times 1 minus 2/3 is 1/3, right? So this is 1/3. And we're going to multiply by 3 over 1. That gives us 9/2. So this sum converges to the value 4.5 or 9/2. Okay. Have you ever wondered how to change a repeating fraction or a repeating decimal into a fraction? Well, that's what we get to do next, using an application of series.